Scientists just discovered that everything we thought we knew about our home galaxy was completely wrong. The James Webb Space Telescope has revealed that the Milky Way isn't the cozy 100,000 light-year wide neighborhood we imagined. It's a massive 200,000 light-year giant packed with hundreds of billions more stars than we ever knew existed. For our entire history, we've been living inside a cosmic metropolis twice the size we thought, surrounded by hidden stellar cities that remained invisible until now. These aren't just distant lights. Each newly discovered star could host planets, moons, and possibly entire worlds teeming with life that we never even knew to look for. But if our own galaxy is twice as big as we thought, what does that mean for our chances of actually finding alien life in our cosmic backyard? On a clear night in the desert, when city lights cannot steal the darkness, you can see it stretching across the sky like a river of light. The ancient Greeks called it the Milky Way because it looked like spilled milk against the black canvas of space. Native Americans saw it as the trail of spirits walking to the afterlife. Every culture that ever looked up gave this ghostly band of light a name and a story, but none of them knew the most amazing truth of all. They were looking at their home from the inside. For thousands of years, humans stared up at this mysterious glow without understanding what they were seeing. The brightest minds in history wondered about its nature. Some thought it was a crack in the heavens where divine light leaked through. Others believed it was a road built by the gods. A few clever thinkers guessed it might be made of distant stars, but they had no way to prove their wild idea. Night after night, generation after generation, the Milky Way hung above them like a cosmic riddle waiting to be solved. The truth began to emerge only when telescopes were invented. Suddenly, that smooth river of light broke apart into countless tiny points. Each point was a star. Millions and millions of stars packed so tightly together that human eyes could not tell them apart. The realization hit like lightning. We were not looking up at some distant object in the sky. We were looking at the galaxy we live inside. Every star we could see, including our own sun, was part of this enormous spinning island of light floating through the darkness of space. But knowing we lived inside a galaxy only made the mystery deeper. How big was this cosmic home? Where did it begin, and where did it end? Trying to measure the Milky Way from inside it was like a fish trying to figure out how big the ocean is while swimming deep underwater. The fish can see water in every direction, but it cannot see the surface or the bottom or the shores. Earth sits buried deep inside our galaxy, surrounded by dust and gas and billions of stars. We cannot step outside to look back and see the whole picture. Scientists tried their best to solve this puzzle. They counted stars in different directions. They measured how bright distant stars appeared. They used every trick they could think of to peek through the cosmic fog that surrounds us. Slowly, carefully, they built a map of our galactic neighborhood. Their best guess was that the Milky Way stretched about 100,000 light-years from edge to edge. 1 light-year is the distance light travels in a whole year, moving at 186,000 miles every single second. 100,000 light-years meant our galaxy was so huge that a beam of light would need 100,000 years to cross from one side to the other. This number seemed almost too big to believe. If you could shrink Earth down to the size of a grain of sand, the Milky Way would still be bigger than the entire United States. Our solar system, which contains the sun and all its planets, would be smaller than a single house in this cosmic country. The numbers made human brains hurt just thinking about them. Yet something whispered that even these impossible measurements might be wrong. The galaxy felt bigger than the math suggested, but proving it seemed hopeless. The problem was simple but deadly serious. Thick clouds of dust drift between the stars like cosmic smoke. This dust blocks light the same way fog blocks your view on a misty morning. When astronomers pointed their telescopes toward the outer edges of the galaxy, they could only see a little way before the dust made everything disappear into darkness. They were like drivers trying to navigate through heavy fog with broken headlights. They could make rough guesses about where they were going, but they could not see the road clearly. For decades, this cosmic fog kept the true size of our galaxy hidden. Telescopes got bigger and better, but they still could not peek through the dusty barriers that blocked the view. Scientists knew there had to be more stars out there in the darkness, but finding them seemed impossible. The Milky Way guarded its secrets well, wrapping itself in veils of dust that no ordinary telescope could penetrate. Then something changed everything. Engineers and scientists worked together to build a new kind of eye for looking at space. Instead of trying to see regular light like human eyes do, this new telescope would see infrared light. Infrared is the kind of light that heat makes. You cannot see it with your eyes, but you can feel it when you hold your hand near a warm stove. The amazing thing about infrared light is that it can pass through dust clouds that stop regular light completely. It was like giving astronomers a pair of magic glasses that could see through cosmic fog. This special telescope was named after James Webb, one of the people who helped send the first astronauts to the moon. The James Webb Space Telescope was built to be the most powerful space telescope ever created. Its main mirror was as wide as a tennis court and covered with gold to make it extra sensitive to infrared light. But the real magic happened when scientists pointed this incredible machine toward the hidden edges of our own galaxy. What they discovered would shock the world and rewrite every astronomy book on Earth. The James Webb Space Telescope began to see things that had been invisible for all of human history. Stars that had been hiding behind thick dust clouds suddenly appeared like candles being lit in a dark room. Entire regions of the galaxy that had been blank empty space in older telescope pictures now blazed with the light of millions of previously unknown stars. The fog was finally lifting, and the true face of the Milky Way was about to be revealed for the first time. Picture a tiny ant crawling around inside the biggest library in the world. The ant wants to know how many books fill this enormous building, but there is one huge problem. The ant cannot fly. It cannot climb to the top of the tallest bookshelf to look around. It cannot even see over the first row of books. All the ant can do is walk along the floor, counting the books it can reach, and try to guess how many more books might be hiding on higher shelves in rooms it has never seen. This is exactly the problem scientists face when trying to measure the Milky Way galaxy. We live inside our galaxy, stuck on a small planet that orbits an ordinary star. Just like that ant on the library floor, we cannot step outside to get a good look at the whole thing. We are trapped inside the very thing we want to measure. When you stand inside your house, you can walk from room to room and count how many rooms there are. But imagine trying to figure out how big your neighborhood is without ever going outside or looking out a window. That is what astronomers have been trying to do with our galaxy for hundreds of years. The problem gets much worse because space is not empty and clean like the inside of a house. Between the stars, huge clouds of dust drift like cosmic smoke. This dust is not like the dust under your bed. These are tiny pieces of rock and ice, smaller than the tiniest grain of sand, floating in the cold darkness between stars. The dust clouds can be bigger than our entire solar system. They stretch for thousands and thousands of miles, blocking light like thick fog blocks your view on a cloudy morning.
When astronomers point their telescopes toward the edge of our galaxy, trying to count stars and measure distances, the dust gets in the way. It is like trying to count cars in a parking lot during a thick fog storm. You can see the cars that are close to you, but the ones farther away disappear into the gray mist. You know there are more cars out there, but you cannot see them or count them. The dust in space does the same thing to starlight, making distant stars fade away until they become invisible. For many years, scientists tried every trick they could think of to see through this cosmic dust. They built bigger telescopes with mirrors as wide as swimming pools. They put telescopes on top of tall mountains where the air is thin and clear. They even sent telescopes into space to get away from Earth's atmosphere completely. Each new telescope could see a little bit farther and a little bit clearer than the ones before. But the dust clouds still blocked their view of the galaxy's outer edges. The dust problem made measuring our galaxy feel impossible. Scientists could count the stars they could see and make careful measurements of how far away those stars were. They could study how fast stars move as they orbit around the center of the galaxy. They could even detect invisible dark matter by watching how its gravity affects the stars they could observe. All of these measurements helped them build a picture of the Milky Way, piece by piece, like putting together a giant jigsaw puzzle with most of the pieces missing. Using all their best measurements and most careful calculations, scientists decided our galaxy was probably about 100,000 light-years across. This number came from adding up all the stars they could see and making educated guesses about the parts they could not observe. It was like trying to figure out how many jelly beans are in a big jar when you can only see the ones pressed against the glass. The scientists knew their number might be wrong, but it was the best answer they could give with the tools they had. But something felt incomplete about this measurement. When scientists looked at other galaxies far away in space, they could see those galaxies completely because they were looking at them from the outside. Many of those distant galaxies appeared much bigger and more spread out than the Milky Way was supposed to be. This made some astronomers wonder if maybe our galaxy was bigger than they thought. Maybe there were lots more stars hiding in the dusty outer regions that no telescope had ever been able to detect. The problem was not that scientists lacked curiosity or clever ideas. The problem was that regular telescopes see the same kind of light that human eyes see. This visible light gets blocked by dust the same way a thick curtain blocks sunlight from coming through a window. No matter how big or powerful a regular telescope was, it still could not see through the dust clouds that surrounded the outer parts of our galaxy. The dust acted like a giant wall that hid huge sections of the Milky Way from view. Scientists needed a completely different approach. They needed a way to see through dust instead of being stopped by it. They needed telescopes that could detect kinds of light that dust cannot block. For years, this seemed like an impossible dream. How could they build an eye that could see through cosmic fog that had been blocking their view since telescopes were first invented?
The answer came from understanding heat. Every warm object gives off infrared light, which is a kind of light that human eyes cannot see but special cameras can detect. The amazing thing about infrared light is that it can pass through dust clouds that stop regular light completely. It is like having X-ray vision that can see through walls. If scientists could build a telescope sensitive enough to detect infrared light from distant stars, they might finally be able to peer through the dust and see the hidden parts of our galaxy. This idea sparked the greatest telescope project in human history. Scientists and engineers from around the world worked together to design and build a telescope unlike anything that had ever existed. This telescope would not just be a little bit better than the ones before it. It would be revolutionary, capable of seeing things that had been completely invisible throughout all of human history. The dust that had hidden the true size of our galaxy for thousands of years was about to meet its match. For more than 50 years, astronomy textbooks around the world taught the same basic fact about our home galaxy. The Milky Way stretches 100,000 light-years from one edge to the other. This number appeared in every science class, every planetarium show, and every documentary about space. Teachers wrote it on blackboards. Students memorized it for tests. Scientists used it in their research papers and computer models. The number 100,000 became as familiar and trusted as knowing that Earth has one moon or that the sun is a star. But this familiar number was built on shaky ground, like a house constructed on sand that looks solid until the first big storm hits. Scientists had calculated this measurement by carefully studying the stars they could see and making their best guesses about the parts of the galaxy hidden behind cosmic dust clouds. They counted bright stars in different directions from Earth. They measured how fast stars orbit around the galaxy's center. They studied the way gravity from invisible dark matter affects the motion of visible stars. Each measurement gave them clues about the galaxy's size and mass. The problem was that all of these measurements came with huge question marks attached. When scientists looked toward the center of the galaxy, thick dust clouds made it almost impossible to see very far. When they looked toward the outer edges, the dust blocked their view even more completely. They were like detectives trying to solve a mystery with only half the evidence available. They could build a reasonable case based on what they could observe, but they knew important clues were still hidden from sight.
Different groups of scientists came up with slightly different answers when they tried to measure the galaxy. Some thought it might be 90,000 light-years across. Others suggested it could be as big as 120,000 light-years. The differences came from using different methods and making different assumptions about the parts they could not see clearly. But most estimates clustered around that familiar number of 100,000 light-years. It seemed like a reasonable middle ground that most scientists could agree on. This measurement meant our galaxy was already almost impossibly huge by human standards. 100,000 light-years is a distance so vast that human brains struggle to understand it. Light travels at 670 million miles per hour, moving faster than anything else in the universe. Even at this incredible speed, light needs 100,000 years to cross from one side of our galaxy to the other. If you could somehow travel at the speed of light, you would still need more time than all of recorded human history to make the journey from edge to edge. To make this size easier to imagine, scientists created comparisons that helped people understand the scale. If the Milky Way were shrunk down to the size of the United States, our entire solar system would be smaller than a single city block. Earth would be too tiny to see without a powerful microscope. The sun, which seems enormous to us, would be just a speck of dust in this cosmic country. These comparisons helped people realize they lived in something truly gigantic, but the numbers still felt manageable in a strange way. 100,000 was a round, neat number that human minds could at least try to wrap around. Scientists also estimated that our galaxy contained about 100 billion stars based on the size measurement. This was another number that appeared in textbooks everywhere. 100 billion stars seemed like more than anyone could ever count, scattered across 100,000 light-years of space. Each star was like our sun, possibly warming planets where life might exist. The math suggested that our galactic neighborhood was already crowded enough to contain countless worlds and maybe even other civilizations looking up at their own night sky. But even as these measurements became accepted facts, some scientists felt uneasy about them. When they studied other galaxies far away in space, many of those distant star cities appeared much larger and more spread out than the Milky Way was supposed to be. Some galaxies contained bright stars scattered across regions that stretched 200,000 light-years or more. This observation raised uncomfortable questions. Why would our galaxy be smaller than many others? Was Earth located in an unusually compact galaxy? Or were the measurements of our own cosmic home somehow wrong? The unease grew stronger when scientists discovered that many galaxies have extended halos of old, dim stars surrounding their bright central regions. These stellar halos are like ghostly suburbs that stretch far beyond the main city of stars. The halos contain stars that formed billions of years ago when galaxies were young and still growing by capturing smaller star groups. If other galaxies had these extended halos,
Maybe the Milky Way had one too, hidden in regions too dusty and dim for telescopes to detect. Advanced computer simulations of how galaxies form and grow suggested that star cities like ours should be larger than the measured 100,000 light-years. According to the models, galaxies build themselves over billions of years by gobbling up smaller groups of stars. This process should create extended regions of scattered stars that stretch much farther than the bright, densely packed central disk where most stars live. The simulations predicted that the Milky Way should have these far-flung stellar suburbs, but no telescope had ever been able to find them.
Some bold scientists began to whisper that the textbook number might be wrong by a huge amount. They suggested that the Milky Way could actually be twice as big as everyone thought, stretching 200,000 light-years from edge to edge instead of 100,000. This possibility would mean our galaxy contained not 100 billion stars, but perhaps 400 billion or even more. The implications were staggering. Everything students learned about their cosmic home would need to be rewritten. But whispers and suspicions were not enough to change scientific textbooks. To overturn 50 years of accepted measurements, scientists would need clear, undeniable proof that the galaxy was actually much larger than estimated. They would need a telescope powerful enough to see through the cosmic dust and count the hidden stars that earlier instruments could not detect. They would need evidence so strong that no scientist could doubt it. That evidence was about to arrive from an unexpected source floating in the cold darkness of space. 1 million miles from Earth, floating in the cold emptiness of space, sits the most amazing telescope humans have ever built. The James Webb Space Telescope looks nothing like the telescopes you might see in movies or science museums. It does not point straight up at the sky through a long tube. Instead, it unfolds like a giant golden flower made of 18 separate mirror pieces that work together as one enormous eye. Each mirror piece is covered in a thin layer of pure gold, making the whole telescope gleam like a treasure chest floating among the stars. The telescope is as wide as a tennis court when all its parts are spread out. Its main mirror measures 21 feet across, which makes it almost 3 times bigger than the famous Hubble Space Telescope that has been taking pictures of space for more than 30 years. But size is not the only thing that makes James Webb special. The real magic happens because this telescope can see kinds of light that human eyes cannot detect. While your eyes see red, orange, yellow, green, blue, and purple light, James Webb sees infrared light, which is the invisible light that heat makes. Everything in the universe that has any warmth at all gives off infrared light. Your body makes infrared light. A warm cup of hot chocolate makes infrared light. Even ice cubes make a tiny bit of infrared light because they are warmer than the coldness of outer space. Stars make enormous amounts of infrared light along with all the visible light they produce. The amazing thing about infrared light is that it can travel through cosmic dust clouds that block regular light completely. It is like having magic glasses that let you see through fog, smoke, and walls. To detect this invisible infrared light, the James Webb Space Telescope has to be kept incredibly cold. The telescope needs to be colder than the coldest winter day you can imagine. It needs to be colder than the ice at the North Pole. In fact, it needs to be almost as cold as space itself, which is 400 degrees below zero. If the telescope got warm, its own heat would create infrared light that would interfere with the faint infrared signals coming from distant stars and galaxies. It would be like trying to listen to a whisper while standing next to a roaring waterfall. To stay this cold, the telescope hides behind a giant sunshade that is as big as a tennis court. This sunshade has 5 layers of special material that reflects heat and light away from the telescope. The sunshade works like a huge umbrella that blocks the heat from the sun, earth, and moon. The side of the telescope that faces the sun stays nice and warm, but the side that faces deep space becomes so cold that the air around it would freeze solid in just a few seconds. The telescope floats at a special spot in space called a Lagrange point, where the gravity from Earth and the sun balance each other perfectly. At this location, the telescope can stay in the same position relative to Earth without using fuel to fight against gravity. It orbits around the sun along with Earth, always staying about 1 million miles away from our planet. This distance puts it 4 times farther from Earth than the Moon, in a region where the sky is always perfectly dark and still. From this cold, dark, quiet place in space, James Webb can stare at the same patch of sky for hours or even days without being disturbed by Earth's atmosphere, city lights, or changing weather. When the telescope points its golden mirrors toward a distant part of the galaxy, it can collect infrared light for so long that it can detect stars too faint and too far away for any other telescope to see. It can spot the glow from a candle on the moon or the heat from a bumblebee at the distance of the moon. But the most incredible thing about James Webb's vision is how it can see through the cosmic dust that has been hiding parts of our galaxy for all of human history. When the telescope looks toward the center of the Milky Way, where thick dust clouds block most visible light, it can peer right through those clouds and see the stars hidden behind them. When it looks toward the outer edges of our galaxy, it can detect the faint infrared glow from distant stars that no previous telescope could ever observe. The telescope does not just take pictures like a camera. It can also split light into different colors to study what stars are made of and how hot they are.
It can measure how fast stars are moving toward us or away from us. It can even detect the faint heat glow from planets orbiting other stars. Every piece of information the telescope collects gets sent back to Earth as radio signals that travel at the speed of light, taking about 5 seconds to make the journey from the telescope to scientists waiting eagerly on the ground.
Scientists had dreamed of building a telescope like James Webb for more than 20 years before it finally launched into space. The project required new technologies that had never been invented before. Engineers had to figure out how to fold a telescope as big as a tennis court, small enough to fit inside a rocket, then unfold it perfectly in space without any astronauts there to help if something went wrong. They had to create mirrors so smooth and precise that if they were expanded to the size of Earth, the biggest bump would be only 6 feet tall. When James Webb finally opened its golden eye and began looking at the universe, it immediately started seeing things that had never been observed before. Ancient galaxies from the early universe appeared in its images, showing what the cosmos looked like billions of years ago. Nearby stars revealed planets and moons in incredible detail, but perhaps most exciting of all, the telescope began to peer into the dusty, hidden regions of our own galaxy that had remained mysterious throughout all of human history. The cosmic fog that had concealed the true size and nature of the Milky Way was finally about to be lifted by this remarkable machine floating in the darkness of space. When James Webb first pointed its golden mirrors toward the outer regions of our galaxy, scientists expected to see more of the same faint, scattered stars that earlier telescopes had detected at the edges of the Milky Way. They thought they might find a few thousand additional dim stars hiding behind cosmic dust clouds. They hoped to get a slightly better count of what was already there. What they discovered instead was so shocking that it made astronomers around the world stop and stare at their computer screens in complete disbelief. The first images that came back from the telescope showed regions of space that had appeared completely empty and black in every previous photograph. These dark zones had been studied by the Hubble Space Telescope and dozens of ground-based telescopes for years. Scientists had pointed their most powerful instruments toward these areas and seen nothing but empty darkness. The regions looked like cosmic deserts where no stars lived, vast stretches of space that marked the lonely edges of our galactic home. But when James Webb looked at these same dark regions with its infrared vision, they suddenly blazed with the light of millions of previously invisible stars. It was like walking into a room that appeared empty and dark, then flipping on a light switch to discover the room was actually packed wall to wall with people who had been standing there all along. The stars had always been there, glowing steadily in the darkness, but cosmic dust had hidden them completely from every telescope that had ever tried to see them. The hidden stars were not just a few scattered points of light sprinkled here and there in the darkness. They formed vast neighborhoods and cities that stretched much farther from the center of our galaxy than anyone had ever imagined possible. Some of these stellar communities contained more stars than entire small galaxies. They had been sitting right next to us, part of our own cosmic home, but invisible until James Webb's special vision finally revealed them. Scientists started counting these newly discovered stars with growing amazement. In one small patch of sky that had looked completely empty before, James Webb found more than 50,000 stars that no human had ever seen. In another region, the telescope revealed dense clusters containing hundreds of thousands of stars arranged in beautiful spiral patterns that had been completely hidden behind dust clouds. Each new image that came back from the telescope contained more surprises, more hidden stellar cities that changed everything astronomers thought they knew about our galaxy. The discoveries kept getting bigger and more incredible. James Webb found entire spiral arms of our galaxy that had been completely unknown before. These arms were like cosmic highways made of stars, stretching for thousands of light years through regions that had appeared empty and lifeless. The newly discovered spiral arms contained young blue stars, old red stars, and everything in between. Some arms were thick and densely packed with millions of stars, others were thin and delicate, like cosmic spiderwebs made of distant suns. But the most shocking discovery came when scientists began to realize just how far these hidden stars extended from the center of our galaxy. The Milky Way was not ending where they thought it did. Instead of reaching a clear boundary at about 50,000 light-years from the center, the newly visible stars kept going and going and going. They stretched twice as far as anyone had ever measured before. They reached into regions of space that were supposed to be empty cosmic wilderness between our galaxy and the next nearest star city. The hidden stars were not randomly scattered through space like cosmic confetti. They were organized into clear structures and patterns that showed our galaxy had grown much larger over billions of years by capturing smaller groups of stars and adding them to its outer regions. James Webb could see the ghostly remains of ancient small galaxies that had been eaten by the Milky Way long ago. Their stars had been scattered into long streams and shells that painted beautiful patterns across the newly revealed outer regions of our galactic home. Some of the hidden stellar populations were incredibly old, containing stars that formed when the universe was young and very different than it is today.
These ancient stars had been wandering through the outer darkness of our galaxy for billions of years, invisible and unknown until James Webb finally spotted their faint infrared glow. They were like cosmic fossils that told the story of how our galaxy had grown and changed over vast spans of time by slowly gobbling up smaller star groups.
Other hidden regions contained surprisingly young stars that were still forming from clouds of gas and dust in the outer reaches of the galaxy. Scientists had thought star formation only happened in the inner, denser parts of the Milky Way, where there was enough raw material to build new suns. But James Webb revealed active star nurseries operating in the distant suburbs of our galaxy, creating bright new stars in regions that were supposed to be too empty and cold for such activity. The telescope also discovered massive streams of stars flowing between different parts of the galaxy, like cosmic rivers. These stellar streams were the scattered remains of small star clusters that had been ripped apart by the Milky Way's gravity over millions of years. The streams created bridges and connections between distant regions, showing that our galaxy was much more interconnected and dynamic than anyone had realized. As scientists added up all the newly discovered stars, the numbers became almost impossible to believe. Regions that were supposed to contain maybe a few million scattered stars actually held hundreds of millions of previously hidden suns. Areas that should have been nearly empty turned out to be packed with stellar populations that rivaled the densest parts of the galaxy's main disk. The Milky Way was not just a little bit bigger than measured before. It was enormously, dramatically, spectacularly larger than anyone had ever dreamed possible. Each new discovery made the picture clearer and more amazing. The galaxy that humans had called home for all of history was actually twice the size that 50 years of careful measurements had suggested. The cosmic island where Earth lived was not a modest collection of 100 billion stars. It was a massive stellar empire containing hundreds of billions of suns, stretching across distances that made the old measurements look tiny and insignificant. The Milky Way had revealed its true face for the first time, and that face was magnificent beyond imagination. When scientists finally finished counting all the newly discovered stars that James Webb had revealed in the hidden regions of our galaxy, the numbers made them feel dizzy. They checked their math over and over again, certain they had made a mistake somewhere. They ran their computer programs multiple times, hoping the calculations would come out differently. But every time they added up all the stars they could now see, they got the same impossible answer. The Milky Way was not 100,000 light-years across like textbooks had taught for 50 years. It was 200,000 light-years from edge to edge. 200,000 light-years. The number felt too big to be real. It meant that everything students had learned about their cosmic home was wrong. It meant that every science book, every documentary, and every planetarium show had been teaching measurements that were only half the true size. The galaxy where humans lived was not just a little bit bigger than expected. It was exactly twice as large as the most careful measurements had suggested. To understand how shocking this discovery was, imagine that you had lived your whole life thinking your house had 10 rooms. You had counted the rooms many times. You had measured the walls and calculated the total size. You were completely sure your house had exactly 10 rooms. Then one day, someone gave you a special pair of glasses that let you see through walls you had never noticed before. Suddenly you realized your house actually had 20 rooms. You had been living in a place twice as big as you thought, with whole sections you never knew existed. This is exactly what happened to our understanding of the Milky Way. The galaxy had always been twice as big as scientists measured, but thick cosmic dust had hidden the outer half from every telescope that had ever tried to observe it. James Webb's infrared vision finally revealed the hidden rooms in our galactic house, showing that we lived in a cosmic mansion instead of the more modest home we thought we knew. The new measurement meant that light needed 200,000 years to travel from one edge of our galaxy to the other. If you could somehow send a message at the speed of light from one side of the Milky Way to the other side, that message would not arrive until 200,000 years had passed. This span of time covers all of recorded human history twice over. It stretches back to when early humans were just learning to use tools and make fire. A beam of light that started crossing our galaxy when the first humans painted pictures on cave walls would just now be reaching the other side. The doubled size meant that every comparison scientists had used to help people understand our galaxy needed to be changed completely. If the Milky Way were shrunk down to the size of the United States, our solar system would be smaller than a single city block, just as before. But now the galaxy would actually be as big as the United States and Canada combined. If Earth were reduced to the size of a grain of sand, the Milky Way would stretch across an area larger than all of North America and South America put together. But the most mind-blowing change was in the number of stars our galaxy contains. Scientists had estimated that the Milky Way held about 100 billion stars based on its supposed size of 100,000 light-years. With twice the size came 4 times the volume of space, and 4 times the volume meant room for many more stars than anyone had ever imagined. The hidden regions revealed by James Webb were not empty cosmic suburbs with just a few scattered stars. They were packed with stellar neighborhoods that contained hundreds of billions of additional suns. The new star count was so large that it made human brains hurt trying to understand it. Instead of 100 billion stars, the Milky Way actually contains somewhere between 300 billion and 400 billion stars. Some estimates suggested the number might be even higher than that. The exact count was hard to determine because James Webb was still discovering new stellar populations in regions that had never been observed before. But every new discovery added millions more stars to the total, 400 billion stars. The number was so huge that it lost all meaning to human minds. If you tried to count to 400 billion by saying one number every second, it would take you more than 12,000 years to finish counting. If every person on Earth counted stars at the same time, working together around the clock, it would still take more than a century to count them all. The Milky Way contained more stars than there are grains of sand on all the beaches of Earth combined. Each of these hundreds of billions of stars was like our sun, a massive ball of burning gas that could warm planets orbiting around it. Most stars probably had planets, just like our solar system has Earth and Mars and Jupiter. If even a tiny fraction of these planets were the right distance from their stars to have liquid water, there could be millions or billions of worlds where life might exist. The doubled size of our galaxy meant that the chances of finding life somewhere else among the stars had suddenly become much, much better. The implications went beyond just having more stars and more possible planets. The larger galaxy meant that everything scientists thought they knew about how the Milky Way formed and grew over billions of years needed to be reconsidered. Computer models that tried to explain how our galaxy developed had been based on the smaller size measurements. With twice the actual size, these models no longer worked correctly. The Milky Way had grown much larger over cosmic time by capturing and eating more small galaxies than scientists had realized. The discovery also changed our place in the cosmic neighborhood. Other nearby galaxies that had seemed much bigger than the Milky Way were now revealed to be more similar in size to our home. The Andromeda Galaxy, our nearest large neighbor, was still bigger than the Milky Way, but not by as much as scientists had thought. Our galaxy was not a small fish swimming in a pond full of giants. It was actually one of the larger and more impressive star cities in our local region of the universe. As the full impact of the discovery sank in, astronomers around the world began to realize they were witnessing one of the most important moments in the history of space science. James Webb had not just found a few more stars hiding in dusty corners of the galaxy. It had revealed that humans lived in a cosmic home twice as magnificent and vast as anyone had ever dared to imagine. The most amazing discovery that came from James Webb's exploration of our galaxy's hidden regions was something that changed how scientists understood the very structure of the Milky Way itself. As the telescope peered deeper into the dusty outer reaches that had been invisible for all of human history, it revealed something that no astronomer had ever expected to find. Our galaxy was surrounded by a massive halo of ancient stars that stretched far beyond the bright spiral arms where most stars live. This stellar halo was like discovering that your house had a huge backyard that you never knew existed. For decades, scientists had focused on studying the main disk of our galaxy, the flat spiral of stars that contains our solar system and most of the bright stars visible in the night sky. They knew this disk was the heart of the Milky Way, where new stars were born and where most of the galaxy's action took place. But they had no idea that this bright disk was surrounded by something much larger and more mysterious. The stellar halo that James Webb revealed was not made of young bright stars like the ones in the galaxy's main disk. Instead, it contained some of the oldest stars in the entire universe, ancient suns that formed more than 10 billion years ago when the cosmos was still young and wild. These elderly stars were much dimmer and redder than the bright blue and white stars that dominated the galaxy's spiral arms. They glowed with a faint, steady light that had been shining since before Earth even existed. The age of these halo stars told an incredible story about the early history of our galaxy. They were cosmic fossils that remembered what the Milky Way was like billions of years ago, long before it became the organized spiral of stars we see today. When these ancient stars first began to shine, our galaxy was probably a chaotic, messy collection of gas clouds and small star clusters that had not yet settled into the neat spiral pattern that exists now. As James Webb mapped more and more of this extended stellar halo, scientists realized it was enormous beyond anything they had imagined. The halo stretched in all directions from the main disk of the galaxy, forming a giant sphere of old stars that surrounded our entire galactic home. The sphere was so large that it extended twice as far from the galaxy's center as the bright spiral arms reached. It was like discovering that the Milky Way wore an invisible crown made of ancient starlight. The halo contained billions of these old, faint stars scattered through a volume of space so huge that it made the main disk of the galaxy seem small by comparison. If the bright spiral disk was like a dinner plate sitting on a table, the stellar halo was like a beach ball that surrounded the entire table. The halo held more space than the spiral arms, but because its stars were so old and dim, no telescope had ever been able to see them clearly until James Webb came along with its incredible infrared vision. But the stellar halo was not just a collection of random old stars floating in the darkness. As scientists studied the patterns and movements of these ancient suns, they discovered that the halo told the story of how the Milky Way had grown over billions of years. The halo stars were not born in our galaxy at all. They were the scattered remains of smaller galaxies that the Milky Way had captured and eaten during its long history of growth. Billions of years ago, when the universe was younger and galaxies were smaller, the Milky Way was surrounded by dozens of tiny star cities, each containing a few million or billion stars. Over cosmic time, the gravity of our growing galaxy reached out and grabbed these smaller neighbors, pulling them in and tearing them apart like a giant cosmic vacuum cleaner. The stars from these destroyed galaxies did not disappear. Instead, they were scattered into long streams and shells that formed the extended halo around our galactic home. James Webb could actually see the ghostly remains of these ancient galactic meals. The telescope revealed long streams of stars flowing through the halo like cosmic rivers, marking the paths where small galaxies had been ripped apart by the Milky Way's gravity. Some streams were thick and bright, showing where large star clusters had been destroyed relatively recently. Other streams were thin and faint, the faded trails of tiny galaxies that had been consumed billions of years ago. The discovery of these stellar streams was like finding the bones of dinosaurs that told the story of ancient life on Earth. The streams were fossils of cosmic history that showed exactly how the Milky Way had grown from a small galaxy into the giant star city it is today. Each stream represented a chapter in our galaxy's biography, a record of conquest and growth that stretched back to the earliest days of the universe. But the stellar halo revealed more than just ancient history. It also showed that the process of galactic growth was still happening today. James Webb found evidence of small galaxies that were being torn apart by the Milky Way's gravity right now, their stars being scattered into new streams that would eventually join the vast halo surrounding our cosmic home. The galaxy was still growing, still reaching out with invisible hands of gravity to capture new star clusters and add them to its collection. The size of the stellar halo explained why the Milky Way turned out to be so much larger than scientists had measured before. The halo was not separate from our galaxy, it was part of the Milky Way, just as much as the bright spiral arms where Earth lived. When astronomers added up all the stars in both the main disk and the extended halo, they got the true size of our galactic home for the first time in history. The halo also revealed something important about the invisible dark matter that makes up most of the mass in our galaxy. Dark matter cannot be seen directly, but its gravity affects the motion of stars and gas throughout the Milky Way. The stars in the halo moved in ways that showed exactly how the dark matter was distributed around our galaxy. The halo stars acted like cosmic lighthouses that illuminated the invisible dark matter structure that held our entire galactic neighborhood together. Understanding the stellar halo changed everything about how scientists thought about galaxy formation throughout the universe. If the Milky Way had grown so large by eating smaller galaxies, then other star cities probably grew the same way. The universe might be full of galaxies surrounded by their own extended halos of ancient stars, the scattered remains of cosmic meals consumed over billions of years of galactic evolution. The discovery that our galaxy was twice as big as anyone had ever measured meant that everything scientists thought they knew about how galaxies form and grow needed to be completely reconsidered. For decades, astronomers had built computer models that tried to explain how star cities like the Milky Way developed over the billions of years since the universe began. These models were like cosmic recipes that showed how galaxies mixed together gas, dust, dark matter, and time to create the beautiful spiral structures we see today. But all of these models had been based on the old measurement that said our galaxy was only 100,000 light-years across. The computer simulations had been designed to create a galaxy of that size, using specific amounts of matter and energy to build spiral arms that stretched exactly that far from the galactic center. When James Webb revealed that the real Milky Way was actually 200,000 light-years across, it was like discovering that a recipe everyone thought made a small cake had actually been making a giant cake all along. Scientists realized that their computer models had been missing huge pieces of the galactic puzzle. The models had successfully explained how the bright inner parts of the galaxy formed, with their dense spiral arms and active star formation regions, but they had completely failed to account for the massive outer regions that contained billions of additional stars scattered through the extended stellar halo. The models were like maps that showed only half the territory they were supposed to describe. The problem went deeper than just getting the size wrong. The discovery of the larger galaxy meant that the Milky Way had somehow managed to gather much more matter during its formation than the computer models predicted was possible. Galaxies grow by pulling in gas from the space around them and by capturing and eating smaller star clusters. But the models suggested there was not enough nearby matter for our galaxy to have grown as large as James Webb had revealed it actually was. This puzzle led scientists to realize that galaxies probably grew much more actively in the past than anyone had understood. The early universe was apparently a much more violent and chaotic place, where galaxies regularly crashed into each other and merged together to form larger star cities. The Milky Way had not grown slowly and peacefully over cosmic time. Instead, it had probably been involved in dozens of galactic collisions and mergers that allowed it to sweep up enough matter to reach its true enormous size. The evidence for this violent history was written in the stars themselves. The ancient stars in the stellar halo that James Webb had discovered were not scattered randomly through space. Instead, they were organized into streams and clumps that showed exactly how the galaxy had grown by tearing apart and absorbing smaller neighbors. Each stream of stars was like a fossil that marked where a small galaxy had been destroyed billions of years ago. Scientists began to realize that the Milky Way was not just one galaxy that had grown large over time. It was actually hundreds of smaller galaxies that had been mashed together into a single giant star city. The bright spiral disk in the center was probably the original core of our galaxy, but everything else had been added later through cosmic collisions and mergers. Our galactic home was like a city that had grown by absorbing all the small towns around it until it became a vast metropolitan area. This new understanding changed how astronomers thought about galaxy formation throughout the entire universe. If the Milky Way had grown so large through mergers and collisions, then other galaxies probably developed the same way. The universe was not full of galaxies that had grown peacefully in isolation. Instead, it was packed with star cities that had fought cosmic wars, eating their neighbors and growing larger through galactic cannibalism. The discovery also explained some puzzling observations that had confused scientists for years. When astronomers looked at very distant galaxies, they were seeing them as they existed billions of years ago because their light took so long to reach Earth. These ancient galaxies often looked much more chaotic and irregular than modern galaxies, with strange shapes that did not fit the neat spiral and elliptical patterns seen in nearby star cities. Now scientists understood why those ancient galaxies looked so messy and disorganized. They were watching galaxy formation in action, seeing star cities in the process of crashing together and merging into larger structures. The smooth, organized galaxies visible in the modern universe were the final products of billions of years of cosmic evolution, the survivors that had grown large and stable after countless mergers and collisions.
The larger size of the Milky Way also meant that our galaxy was much more important in the local cosmic neighborhood than scientists had realized. When astronomers had thought our galaxy was relatively small, it seemed like a minor player compared to the giant Andromeda galaxy, our nearest large neighbor. But with the true size revealed by James Webb, the Milky Way was actually much closer to Andromeda in mass and importance. This discovery changed predictions about what would happen when our galaxy and Andromeda eventually collide in about 4 billion years. Instead of Andromeda being the dominant partner that would swallow up our smaller galaxy, the collision would be more like a merger between two similar-sized star cities. The final result would be a truly enormous elliptical galaxy that combined the best features of both spiral neighbors. The new understanding of galaxy formation also had implications for finding life elsewhere in the universe. Larger galaxies with more violent formation histories would have more opportunities to spread heavy elements like carbon, oxygen, and iron throughout their star-forming regions. These elements are essential for building rocky planets and supporting complex life. A galaxy that had experienced many mergers would be better mixed and more likely to contain numerous worlds where life could develop. But the most profound change was in how scientists understood the relationship between galaxies and the invisible dark matter that makes up most of the mass in the universe. The computer models had suggested that dark matter forms enormous halos around galaxies, but the models based on the smaller Milky Way size had underestimated how large and massive these dark matter halos actually were. With the true size of our galaxy revealed, scientists realized that the Milky Way sits at the center of a dark matter halo that stretches even farther than the stellar halo James Webb had discovered. This invisible structure contains most of the mass in our galactic neighborhood and controls how our galaxy interacts with its surroundings. Understanding the real size of both the visible galaxy and its dark matter halo was essential for figuring out how star cities like ours fit into the larger cosmic web that connects all structures in the universe. The discovery that the Milky Way was twice as large as anyone had ever measured completely changed how our galaxy fit into the cosmic neighborhood. For decades, astronomers had thought of our galactic home as a medium-sized star city in a region of space dominated by much larger galaxies. The Andromeda galaxy, our nearest big neighbor, had seemed like a giant compared to our supposedly modest collection of 100 billion stars. But James Webb's revelation that we actually lived in a galaxy containing 400 billion stars suddenly made our cosmic neighborhood feel much more crowded and competitive. Before the size discovery, the Milky Way had been like the smaller house on a street full of mansions. Andromeda appeared to be about twice as massive as our galaxy, with roughly 200 billion stars compared to our supposed 100 billion. This size difference had made scientists think that when the two galaxies eventually crashed into each other in about 4 billion years, Andromeda would be the dominant partner.
basically swallowing up our galaxy like a large fish eating a smaller one. But the new measurements changed everything about this cosmic collision prediction. With 400 billion stars instead of 100 billion, the Milky Way was suddenly revealed to be much closer in size to Andromeda than anyone had realized. The collision would not be a case of a giant galaxy eating a small one. Instead, it would be more like two similarly sized star cities merging together to create something even more magnificent than either galaxy could be on its own. The space between our galaxy and Andromeda, which had seemed comfortably vast when astronomers thought we lived in a smaller galaxy, now felt relatively cramped. The distance between the two galaxies is about 2.5 million light-years. This might sound like an enormous gap, but when compared to the newly discovered size of both star cities, the separation was only about 12 times the diameter of each galaxy. It was like discovering that two large cities were much closer together than anyone had realized.
This closer relationship meant that the two galaxies were already beginning to influence each other through their gravity, even though they were still millions of years away from actually touching. The gravitational pull between the Milky Way and Andromeda was slowly accelerating both galaxies toward their eventual meeting. Computer simulations showed that the collision was now predicted to be more violent and spectacular than scientists had previously calculated because both galaxies were more massive than the models had assumed. The larger size of our galaxy also changed how astronomers understood the entire local group of galaxies that includes the Milky Way, Andromeda, and about 50 smaller star cities scattered through the same region of space. The local group had seemed to be dominated by Andromeda, with our galaxy playing a secondary role. But the new measurements showed that the Milky Way and Andromeda were actually co-leaders of this cosmic community, two roughly equal giants that shared control of the gravitational environment. This discovery had important implications for the smaller galaxies in our neighborhood. Tiny star cities like the Large and Small Magellanic Clouds, which orbit around the Milky Way like cosmic pets, were now revealed to be much smaller compared to our galaxy than anyone had realized. Our galactic home was not just a little bit bigger than these satellite galaxies. It was enormously, overwhelmingly larger, containing hundreds of times more stars than its small companions. The relationship between our galaxy and these smaller neighbors also became clearer. The Milky Way's much larger size meant it had a much stronger gravitational pull than scientists had calculated. This stronger gravity was slowly tearing apart some of the smaller galaxies, stripping away their stars and adding them to our galaxy's extended halo. The process was happening so slowly that it was invisible to human observers, but over millions of years some of our small galactic neighbors would be completely absorbed into the Milky Way. Understanding our galaxy's true size also helped explain some mysterious observations that had puzzled astronomers for years. High-speed clouds of gas had been detected moving through the space around our galaxy at velocities that seemed too fast for the Milky Way's supposed gravitational pull to control. But with the larger galaxy size came much more mass, and much more mass meant much stronger gravity. The fast-moving gas clouds were actually being pulled around by our galaxy's gravity, which was much more powerful than anyone had realized. The discovery also affected how scientists thought about the ultimate fate of our local group of galaxies. Eventually, over tens of billions of years, the gravitational attraction between all the galaxies in the region would cause them to merge together into one enormous elliptical galaxy. Previous calculations had suggested this final merged galaxy would contain about 300 billion stars, formed mostly from Andromeda, with the Milky Way providing a smaller contribution. But the new size measurements showed that the final merged galaxy would be much larger and more impressive than predicted. Instead of 300 billion stars, it would contain at least 600 billion stars, possibly more. This future galaxy would be one of the largest star cities in our region of the universe, a cosmic metropolis that dwarfed anything that existed today in our local cosmic neighborhood. The timing of the merger between our galaxy and Andromeda also changed slightly with the new size measurements. Larger galaxies with more mass would approach each other faster due to stronger gravitational attraction. Computer simulations suggested that the collision might happen a few 100 million years sooner than previously calculated, though 4 billion years was still the best estimate for when the galaxies would begin their spectacular cosmic dance. But the most important change was in how the collision itself would unfold. When two similarly sized galaxies crash together, the result is much more complex and beautiful than when a large galaxy simply absorbs a smaller one. Both spiral structures would be disrupted and stretched into long tidal tails of stars. The central regions would merge to form a bright galactic core surrounded by shells and streams of stars scattered in intricate patterns. The final product of this merger would not look like either of the original spiral galaxies. Instead, it would be a giant elliptical galaxy with a smooth, rounded shape that contained the combined heritage of both the Milky Way and Andromeda. Future astronomers living in this merged galaxy would inherit a cosmic home twice as magnificent as anything we can see today, a star city so large and diverse that it would take hundreds of thousands of years for light to cross from one edge to the other. This future galaxy would contain regions with stars from both the ancient Milky Way and the ancient Andromeda, cosmic neighborhoods where the stellar populations would tell the story of the great merger that created their galactic home. It would be a living monument to the discovery that our galaxy was always much larger and more important than anyone had ever dared to imagine. When scientists realized that our galaxy contained 400 billion stars instead of 100 billion, the implications for finding alien life became almost overwhelming to think about. The search for extraterrestrial intelligence had already been one of the most exciting challenges in science, but the discovery that there were 4 times more stars to search through suddenly made the possibility of success seem much more likely. Every additional star was like adding another ticket to a cosmic lottery, where the prize was discovering we are not alone in the universe. For decades, scientists involved in the search for extraterrestrial intelligence, known as SETI, had been pointing radio telescopes toward nearby stars, listening for signals that might indicate the presence of alien civilizations. The project required enormous patience because the searchers had to examine thousands of stars one by one, spending hours or days listening to each target for any hint of artificial radio transmissions. With only 100 billion stars estimated to exist in our galaxy, the task already seemed impossibly large. But the revelation that our galaxy actually contained 400 billion stars meant that SETI researchers were facing a search space 4 times larger than they had ever imagined. The good news was that this dramatically increased the chances that intelligent life existed somewhere among those distant suns. The challenging news was that finding those civilizations would be like searching for specific people in a city that had suddenly grown from 1 million residents to 4 million residents overnight. The mathematics of alien detection changed completely with the larger number of stars. Scientists had calculated that if intelligent life was extremely rare, developing on only 1 star system out of every billion, there should still be about 100 alien civilizations in our galaxy based on the old star count. With 400 billion stars, that same level of rarity would mean 400 intelligent civilizations sharing our galactic neighborhood. If life was more common, developing around 1 star out of every million, there could be 400,000 alien societies scattered throughout the Milky Way. These numbers made the search for alien signals seem much more promising, but they also made the task much more complex. Instead of listening to 100 billion potential target stars, SETI researchers would need to monitor 400 billion stellar systems. Even if they could examine 1 star per second around the clock, it would take more than 12,000 years to check every possible location where aliens might be transmitting signals toward Earth. The newly discovered regions of our galaxy were particularly intriguing targets for alien hunters. The ancient stars in the extended stellar halo had been shining for more than 10 billion years, giving any planets around them enormous amounts of time to develop complex life and eventually intelligent civilizations. If aliens existed around these old stars, they could have been developing their technology and culture for twice as long as Earth has even existed as a planet. Such ancient civilizations might have capabilities that would seem like magic compared to human technology. They could have learned to harness the energy of their entire star system, building massive structures around their sun to collect every bit of light and heat it produced. They might have developed space travel so advanced that they could journey between stars as easily as humans travel between cities. Some of these ancient aliens could have established colonies throughout their region of the galaxy, creating networks of worlds connected by technologies we cannot even imagine. The younger stars that James Webb had discovered in the outer regions of our galaxy presented different but equally exciting possibilities for alien life. These stars were actively forming new planets from the disks of dust and gas that surrounded them. If intelligent life was common in the universe, some of these brand new planetary systems might already be developing their first simple life forms. In a few billion years, these worlds could host their own alien civilizations looking up at their night sky and wondering if anyone else was out there. The search for alien signals was not the only way that the expanded galaxy size affected the hunt for extraterrestrial life. Astronomers had also been looking for indirect signs of alien civilizations by searching for artificial structures or modifications that advanced aliens might make to their star systems. A civilization that had learned to build massive solar collectors around their star would cause that star to dim and flicker in characteristic patterns that telescopes could detect from thousands of light years away. With 4 times more stars to examine, the chances of finding these artificial signatures increased dramatically. Somewhere among the 400 billion suns in our galaxy, there might be dozens or hundreds of stars that showed clear signs of alien engineering. The James Webb Space Telescope itself was perfectly designed to detect the infrared heat signatures that massive alien construction projects would produce. The same instrument that had revealed the true size of our galaxy might also be the first to spot definitive proof of alien intelligence. The expanded galaxy also meant that alien civilizations might be much closer to Earth than anyone had realized.
With more stars packed into the space around our solar system, the nearest alien society could be hundreds or thousands of light-years closer than previous estimates suggested. Instead of the closest aliens being tens of thousands of light-years away, they might exist within just a few thousand light-years of our sun.
This closer proximity would make communication with alien civilizations much more practical. Radio signals traveling at the speed of light would take thousands of years to cross the distance instead of tens of thousands of years. While this was still a very long time by human standards, it was short enough that civilizations could potentially exchange messages over the course of their existence. Humans could send a signal to nearby aliens and receive a response within the lifetime of our technological civilization. The discovery also raised new questions about why we had not detected alien signals already. With potentially 400,000 or more intelligent civilizations in our galaxy, at least some of them should be transmitting radio signals, laser beams, or other communications that human technology could detect. The fact that we had not found any obvious alien transmissions despite decades of searching was puzzling given how crowded with life our galaxy might actually be. Some scientists suggested that alien civilizations might be using communication technologies that humans had not yet developed or learned to recognize. Advanced aliens might communicate using gravitational waves, quantum entanglement, or other exotic methods that would be invisible to current human detection equipment. Or they might be deliberately avoiding detection, choosing to remain hidden until younger civilizations like humanity proved they were ready for contact. The larger galaxy also meant that if hostile alien civilizations existed, Earth was potentially at greater risk than anyone had realized. With 4 times more locations where dangerous aliens might evolve, the chances of encountering a civilization with harmful intentions increased along with the chances of finding friendly neighbors. However, most scientists remained optimistic that any civilization advanced enough for interstellar travel would likely be peaceful, having learned to solve the social and technological challenges that currently threaten human survival. The discovery that our galaxy was twice as large as scientists had measured also revealed important clues about one of the biggest mysteries in the universe: dark matter. The invisible substance that makes up most of the mass in space had puzzled astronomers for decades because they could detect its gravitational effects but could not see it directly. The larger size of the Milky Way provided new evidence about how this mysterious matter was distributed throughout our galactic neighborhood and how it influenced the formation of stars and planets. Dark matter does not give off any light that telescopes can see. It does not absorb light or block the view of stars behind it. The only way scientists know dark matter exists is by watching how its gravity affects the things they can observe. Stars at the edges of galaxies move faster than they should if only the visible matter was providing the gravitational pull needed to hold them in orbit. Something invisible and massive must be out there tugging on the stars with its gravity to make them move so quickly. Before James Webb revealed the true size of our galaxy, scientists had built computer models that tried to explain how dark matter was arranged around the Milky Way. These models suggested that our galaxy sat at the center of a huge sphere of dark matter that stretched much farther into space than the visible stars. The dark matter halo was supposed to contain about 10 times more mass than all the stars and gas in the galaxy combined, making it the dominant component of our cosmic neighborhood. But the models had been based on the assumption that the visible galaxy was only 100,000 light-years across, when the real size turned out to be 200,000 light-years. With stars scattered through regions that were supposed to be empty space, scientists realized their dark matter models needed major changes. The visible galaxy was much larger than expected, which meant the invisible dark matter halo around it was probably even more massive and extensive than anyone had calculated. The newly discovered stars in the outer regions of our galaxy provided scientists with perfect tools for studying the invisible dark matter around them. These distant stars acted like cosmic lighthouses that revealed the presence and distribution of dark matter through their orbital motions. By carefully measuring how fast these stars moved and in what directions they traveled, astronomers could map the invisible gravitational field that was pulling on them. The results were surprising and exciting. The stars that James Webb found in the extended stellar halo were moving in patterns that showed the dark matter around our galaxy was not smoothly distributed like a perfect sphere. Instead, the dark matter was clumped and structured, with dense regions connected by thinner streams and filaments. The invisible matter formed a complex web that extended far beyond the visible edges of our galaxy. Some of the stellar streams that James Webb discovered were being stretched and bent by invisible concentrations of dark matter that no previous telescope had been able to detect. The stars were following curved paths through space as they responded to the gravitational pull of dark matter clumps that contained millions of times more mass than our sun. These hidden concentrations of invisible matter were like cosmic mountains that deflected the orbits of passing stars without revealing their presence in any other way. The distribution of dark matter around our galaxy also explained why the Milky Way had been able to grow so much larger than the old measurements suggested. Dark matter provided the gravitational scaffolding that allowed our galaxy to capture and hold on to the smaller star groups that it had absorbed over billions of years. Without the invisible matter acting like cosmic glue, many of these smaller galaxies would have escaped back into intergalactic space instead of being incorporated into our growing galactic home. The dark matter halo around the Milky Way turned out to be enormous, stretching at least 400,000 light-years from the galactic center and possibly much farther. This invisible structure contained enough mass to account for the orbital motions of all the newly discovered stars, while also providing the gravitational influence needed to hold our entire galaxy together. The dark matter halo was like a cosmic foundation that supported everything visible in our galactic neighborhood. Understanding the true size and distribution of dark matter around our galaxy had important implications for finding this mysterious substance in laboratory experiments on Earth. Scientists had been building increasingly sensitive detectors that might be able to catch individual dark matter particles as they passed through our planet. The new measurements of how much dark matter surrounded us and how it was distributed could help these experiments figure out where and when they were most likely to detect the elusive particles. The larger dark matter halo also affected predictions about what would happen when our galaxy eventually collided with the Andromeda galaxy in about 4 billion years. The collision would not just involve the visible stars and gas from both galaxies. The massive dark matter halos surrounding each galaxy would also crash together, creating gravitational disturbances that would reshape the entire local group of galaxies. The final merged galaxy would sit at the center of a dark matter halo even more massive and extensive than either of the original structures. Dark matter research was also connected to some of the most fundamental questions in physics about the nature of space, time, and matter itself. The mysterious substance might be made of particles that had never been detected in any laboratory experiment. These particles could have properties that would revolutionize our understanding of how the universe worked at its most basic level. Studying the dark matter around our galaxy might provide clues that would help physicists solve some of the deepest mysteries about the fundamental nature of reality. The distribution of dark matter throughout our galaxy also influenced where stars formed and how planetary systems developed. Regions with more dark matter provided stronger gravitational pull that could compress gas clouds and trigger the formation of new stars. The invisible matter helped determine which parts of the galaxy would be rich in stars and planets, and which regions would remain relatively empty and cold. Scientists realized that the dark matter around our galaxy might have played a crucial role in making Earth and the solar system possible. The gravitational influence of dark matter helped shape the conditions in our region of the galaxy billions of years ago, affecting everything from the chemical composition of the gas that formed our sun to the orbital dynamics that allowed rocky planets like Earth to develop stable climates suitable for life. The James Webb discovery had revealed that we lived not just in a galaxy twice as large as expected, but in a cosmic environment dominated by invisible forces that shaped everything from the formation of stars to the possibilities for life throughout our galactic home. The visible universe that we could see with our eyes and telescopes was just the small bright tip of a much larger and more complex cosmic iceberg made mostly of mysterious dark matter. The discovery that our galaxy was twice as large as everyone had thought meant that astronomy textbooks around the world would need to be completely rewritten. For more than 50 years, students in classrooms from elementary school to graduate programs had learned the same basic facts about their cosmic home. The Milky Way contains 100 billion stars. It stretches 100,000 light-years from edge to edge. These numbers had been printed in millions of textbooks, repeated in countless documentaries, and taught to generations of students who trusted that science had figured out the basic dimensions of our galactic neighborhood. But James Webb's revelation that the galaxy actually contained 400 billion stars spread across 200,000 light-years meant that half a century of science education had been based on measurements that were only partially correct. Every astronomy textbook would need new chapters. Every science museum would need to update their displays. Every planetarium show would need revised scripts that reflected the true magnificence of our cosmic home. The task of updating all this educational material was enormous. Publishers would need to recall old textbooks and print new editions with corrected numbers and updated diagrams. The old illustrations showing the Milky Way as a modest spiral galaxy would be replaced with images depicting a much larger and more impressive star city. Teachers would need to learn the new measurements and explain to their students why everything they had been taught before was incomplete. Elementary school students who had memorized that our galaxy contained 100 billion stars would need to learn that the real number was 4 times larger. High school astronomy classes that had spent weeks studying galactic structure would discover that the structure was actually much more complex and extensive than their textbooks had described. College students writing research papers about galaxy formation would find that many of their sources contained outdated information that no longer matched the observational evidence. But the changes went far beyond just updating numbers in textbooks. The larger galaxy size affected almost every topic in astronomy education, Lessons about stellar evolution would need to include information about the ancient stars discovered in the extended halo regions. Units on planetary formation would have to discuss the increased likelihood of finding habitable worlds among the newly revealed stellar populations. Classes about the search for extraterrestrial life would need to address how the expanded galaxy changed the odds of detecting alien civilizations. Science museums faced the challenge of redesigning entire exhibits that had been built around the old galactic measurements. Interactive displays that allowed visitors to take virtual journeys across the Milky Way would need to be reprogrammed to reflect the actual size of the trip. Scale models that showed our galaxy compared to other nearby star cities would require new proportions that accurately represented our cosmic neighborhood. Planetarium shows presented particular challenges because many of them used sophisticated computer simulations that had taken years to develop based on the previous size estimates. These digital recreations of our galaxy would need to be completely rebuilt using the new measurements. The process would require teams of programmers and artists working for months to create accurate visualizations of the newly discovered stellar populations and extended galactic structures. The impact on scientific research was equally dramatic. Thousands of research papers published over the decades had used the old galactic size estimates in their calculations and conclusions. While the basic science in these papers remained valid, many of the numerical results would need to be recalculated using the correct measurements. Graduate students would face the daunting task of updating their dissertation research to account for a galaxy that was fundamentally different from what they had started studying. Computer models that simulated galactic evolution would require major revisions. These complex programs had been designed to recreate how the Milky Way formed and grew over billions of years, but they had been calibrated using the incorrect size measurements. Astronomers would need to rebuild their simulations from the ground up, incorporating the newly discovered stellar populations and the extended dark matter halo that surrounded our much larger galaxy. The changes also affected how astronomy was taught at the most basic level. Elementary school teachers who had used simple analogies to help children understand galactic scales would need new comparisons that accurately reflected the true size of our cosmic home. The old comparison that described our solar system as a grain of sand in a galaxy the size of North America would need to be updated to show that the galaxy was actually twice as large as the continental United States. International space agencies faced the challenge of updating their educational materials and public outreach programs. NASA's website, which received millions of visitors each year seeking information about our galaxy, would need comprehensive updates to reflect the new measurements. Educational videos that had been watched by students around the world would become outdated overnight, requiring new productions that incorporated the latest discoveries. The discovery also highlighted how scientific knowledge continues to evolve even for seemingly basic facts about our universe. Students learning about the new galactic measurements would understand that science is not a collection of fixed truths but an ongoing process of discovery that constantly refines and improves our understanding of the cosmos. The textbook changes would serve as a powerful example of how new technology and better observations can revolutionize even well-established scientific knowledge. Professional astronomers faced their own educational challenges as they worked to understand the implications of the larger galaxy size. Conferences and symposiums would need to be organized where experts could share their analysis of the James Webb data and discuss how the discovery affected different areas of galactic research. Graduate programs would need to develop new courses that covered the extended stellar halo and its implications for galaxy formation theories. The changes rippled through related fields of study as well. Astrobiology courses would need to address how the increased number of stars affected calculations about the likelihood of life elsewhere in the galaxy. Physics classes discussing dark matter would incorporate the new information about the extended dark matter halo surrounding our galactic home. Even philosophy courses that explored humanity's place in the universe would need to consider what it meant to live in a cosmic home twice as large as previously imagined. But perhaps the most important change was in how the discovery would inspire a new generation of students to pursue careers in astronomy and space science. Young people learning that humanity's understanding of even our own galaxy could change so dramatically in their lifetime would realize that there were still incredible discoveries waiting to be made. The textbook revisions would not just update old information, but would spark curiosity about what other cosmic mysteries remain to be solved by future generations of scientists armed with even more powerful telescopes and more sophisticated techniques for exploring the universe.